Hello and welcome back to Calculus 1, section 2.5, limits at infinity. So now we are going to observe limit x goes to positive or negative infinity of f of x, which will give us either the finite limit L or it will give us the positive or negative infinity. So, or does not exist. That's also possible. Very few of these are, well, not very few, infinite amount of examples, but you will run into very few of these that does not exist in 2.5. So what is the idea here? So you are going to observe limits as x goes to infinity. We can practice this, right, graphically on exponential function. So what you have here is just standard f of x equals, let's say, e to the x. You can put 2 to the x or whatever. Just e to the x is fine. Observe what's happening as your limit x goes to negative infinity of e to the x. What is happening to the y value as x goes to negative infinity? Yes? It approaches 0. Very good. It approaches 0. So you have to picture yourself walking on this line and just worrying about your elevation, right? Your feet. That's a big foot right there. Your feet are measuring the value of the limit. So what is the limit at 0? Limit is 1, right? Because the y value is 1. You can compute any point by simply plugging in the value, but as you go to infinity, the line falls into the y value of 0. So that's that part. Now, we are going to take a look at the other limit, other side. So limit x goes to positive infinity. You can just say infinity. Right? And what do you get for this one? You get positive infinity. Exactly. So this kind of motion can be decomposed, motion to the right and motion up forever. So this is your positive infinity where x goes, and this is your positive infinity where y goes, which is the solution of the limit. So this one function, I took care of two of the cases that we have most of the time. And the top case, when you have that the limit at infinity is giving you a finite value L, that's the definition for horizontal asymptote. Your exponential function has asymptote at y equals 0, which is this value here. So now we are going to define that. We are actually just, completing what you guys learned in your pre-calculus course. You learned vertical asymptotes, horizontal asymptotes, slant asymptotes, and you also learned the end behavior of the function. Last class, in 2.4, we covered vertical asymptotes. The rest of the things from that list we are covering now. So, definition for horizontal asymptote. Definition for horizontal asymptote. If limit x goes to positive or negative infinity of f of x is equal to L, meaning is a finite number, like 0 or 1 or 3/2. So if the limit is equal to a finite value L, then f of x has a horizontal asymptote at y equals to L. So now you have the limit definition for vertical and horizontal asymptote. Since we determined earlier that limit as x goes to negative infinity of e to the x is equal to 0, we have the horizontal asymptote at y equal 0. And we can see it. I mean, there is a horizontal asymptote on the x-axis. So that's it. I mean, there is nothing else in terms of the horizontal asymptote. You have the definition, and now you just apply it. Now, remember how you used to check one-sided limits for vertical asymptote, and if any of those was infinity, you had the vertical asymptote. If it ends up being a number, it's an open circle, right? So that was yesterday. Now, you will be checking positive infinity, but you also need to check negative infinity. You can't just check one and not check the other, because here's your e to the x example where one side goes, right? So this is the horizontal asymptote. Now, we'll come back to this when we do problems that take everything on. The next part is the end behavior of the function. So end behavior of f of x. For this, this is not XY coordinate system. This is just like a chart, all right? Because each function that we are going to consider in end behavior part is going to have one of these endings. And you can fit a lot of functions here. Now, sure, you might have horizontal asymptote, so this will be coupled with e to the x. Sure. This would also be coupled with square root of x. It will be coupled with ln, and so on. So there are, but for polynomials, these two give you positive x squared, bottom two negative x squared. Diagonal ones give you x cubed, or any x to the even number, odd. So these guys are odd exponents, and these guys are even exponents for polynomials. So this is what the end behavior means. Let me just draw real quick over here, x squared function. So what do I mean by end behavior? I mean, what is the behavior of these two arrows, right? Where is this graph tend as x goes to infinity or negative infinity? So now that we have understanding that these are just possible endings of the function, we define each one of these. So this one is defined as the limit x goes to negative infinity of f of x, which gives us the positive infinity because it goes up. And the one on the bottom is the limit of f of x that gives us negative infinity in the answer as x goes to negative infinity, because it looks downwards towards negative infinity. So that's why the negative infinity is the answer for this. Over here I have limit x goes to positive infinity, right, of f of x, and the answer is positive infinity because it goes up. And the one on the bottom is the limit x goes to positive infinity of f of x. That gives us negative infinity as the answer because it goes downwards. Now, this is the end behavior of the function which you learned already in your pre-calculus course, but you haven't used limits to give a concrete definition to it. You just said as x tends to positive infinity, y tends to positive infinity, right? And that was describing this. But now, in terms of the limit, we can do much more concise definition. So that would be end behavior of these functions. And now I can finally do a full problem to examine e to the x. I promised for the last time, okay? So if I have f of x equal e to the x, and I know what the graph looks like, which is this, on the left-hand side, when I take the limit as x goes to negative infinity of e to the x, and I get 0, that is the horizontal asymptote at y equals 0. As I take the other limit, as x goes to positive infinity of e to the x, I will get positive infinity. And that is just the end behavior, meaning it goes forever up like that. So this would be the full problem, the full analysis of the quote-unquote ends of e to the x. So one end will settle at the asymptote, horizontal asymptote, and the other end will grow without a bound. So now you take your you take the concept and apply it to any function under the sun. And I did talk about this last time. I did warn you that there is no way that I can do every possible example of every function out there, because simply there is thousands upon thousands of those. So you are supposed to learn the concept. For instance, you are asked to graph a polynomial, f of x equals, I don't know, x squared minus 3x plus 2, whatever. You don't really care exactly where this polynomial is. You know that a is equal to 1, which is bigger than 0, it opens up. And that's good enough. You don't even have to worry about the vertex, because you know that the graph will look like this. So you can put coordinate system anywhere. It really doesn't matter, because this left end will pull forever to the left and up, and the right corner will pull forever to the right and up. So it doesn't matter where you place these axes, actually, and if you draw this exactly where it's supposed to be, because domain is infinite for all polynomials. And we can quickly write. So the only thing that was important here was this a. It opens upwards, right, because a is positive. So now we look at the left and right, right? So x, limit x goes to negative infinity of our function. And we see we get positive infinity because it points in the positive y direction, points up. And then limit x goes to infinity of f of x is also positive infinity. Neither of these two gave us finite value, which means there is no horizontal asymptote, right? No how. No horizontal asymptote. We just have end behavior. And end behavior says goes up forever, right part of the graph goes up forever. Where for exponential function, as you can see, left part of the graph settles at the asymptote, right part of the graph goes up forever. And you can match that to the picture immediately. f of x equals to ln x. Okay, we are going to draw this. Does it even make sense to ask what is happening as limit goes to negative infinity? Let me repeat that question. Does it even make sense to ask what is the limit x goes to negative infinity of ln x? Does it make sense to ask the question? No. Why no? Why does this make no sense? Very good. Mathematical answer to what you said, to phrase it in mathematical terms, domain is 0 to positive infinity. So if negative infinity is not in the domain, you can't go there. Remember that we talked about Romeo and Juliet, right? The red arrow and the blue arrow walking on the line to meet at the point. There's nothing to walk on here. There's no function. There's no line. Domain for ln, this is why we study it in pre-calculus, is 0 to positive infinity. This question makes no sense. There is no function that goes towards infinity to check its behavior. You know, this would be the same thing on as asking a question, what's south of South Pole? Right? Makes no sense even to ask that. And some people in advanced physics even argue that there is no sense in asking what is there before Big Bang, because time and space begins at the Big Bang. It's an irrelevant question, what is before Big Bang, right? So we don't get to ask the question for negative infinity. For positive infinity, sure, right? We are going to say limit x goes to positive infinity of ln x, and the answer is positive infinity. Very good, because it always goes up, right? This end of the line, which shoots towards positive infinity in x, will also go always up, which is positive infinity on y. Great. We exhausted both possibilities. The negative infinity question you can't ask at all, and the positive infinity gave us positive infinity, so no horizontal asymptote. No ha. There we go. No horizontal asymptote. Now we have vertical asymptote present, so we can, let's review briefly. How about green? Review 2.4. Limit x goes to 0 plus. I have to approach from the right. There is nothing on the left of 0. I can't approach from the left. There's no function on that side. So 0 plus must be used. In this case, of ln x is equal to negative infinity, which says vertical asymptote at x equals 0. So for vertical asymptotes, you are looking for answer to be infinity to claim asymptote. For horizontal asymptote, you are looking for non-infinity answer. You want the finite value, because that is your. So for vertical asymptotes, asymptote is given here. And for horizontal asymptote, asymptote is given if this is finite value L, it's given there. All right, good. So that's that part on horizontal asymptotes, and then also we reviewed a little bit of this one. Now, there is another creature called slant asymptote, which is going to stay unchanged from what you learned in your pre-calculus class. I have nothing to add to that discussion. Slant asymptote happen only when you have a rational function such that the degree, the leading degree in the numerator is by 1 bigger than the leading degree of the denominator. So, rational function is going to be given, let's say r of x, is going to be given as p of x divided by q of x, where p of x and q of x are polynomials and q of x is not 0. Right? So that's the rational function. Example of the rational function. So examples. 1 over x as the cheapest one, right? Well, you can have x minus 3 divided by x squared plus 8, or x cubed plus x squared minus 1 divided by x squared plus 2. If you learned your stuff well in pre-calc, you know that this is the one that has the slant asymptote. Maybe some of you learned it as oblique asymptote, because the degree in the numerator is by 1 bigger than the degree in the denominator. When you divide them, you get the linear line. Guys, slant asymptote, use the common sense. Slant asymptote is the linear line mx plus b. Mx to the first power. So when you do the long division of polynomials, when you divide x cubed by x squared, you are getting x to the first power. If you have x to the fourth divided by x squared, the answer is x squared, and there are no asymptotes that look like this. Can we all agree on that now? So there is a reason. It's not an arbitrary rule that you have to memorize, y degree in the numerator has to be bigger by 1. It is exactly because of the fact when you do the long division, it falls into mx plus b, which is a linear line like that. And that's called the slant asymptote. So now slant asymptote is the asymptote y equal mx plus b, and so slant asymptote exists only when degree of p of x is equal to degree of q of x plus 1. So you see that the degree of q has to be smaller, and you add 1, and it equals the degree, right? So, top is bigger by 1. That's the fastest way to memorize it. Top bigger by 1, right? So now if I take the example that I already have, I just, put whatever, and that's what we got. So, procedure is do the long division. Of polynomials. All right, so we have to divide x squared plus 2 into x cubed plus x squared minus 1. x squared goes into x cubed x times. And then we multiply it back. X times x squared is x cubed. X times 0x is positive 0x squared. And x times 2 is positive 2x. Now, when we subtract this, we put parentheses and subtract. The first guys cancel. X squared minus 0 squared is x squared. And then we have minus 2x and minus 1. X squared goes into x squared plus 1 times. We don't have to compute anything else. It's always a two-step division. The first step is going to give us the mx term, and then the second division step gives us plus b. We don't care about the remainder. We don't care about anything else. So in this case, the slant asymptote is at y equals x plus 1. So if I am to sketch this function quickly, I will say, all right, there is a slant asymptote at x plus 1, so that's here. That's the slant asymptote. Do I have a vertical asymptote? And the answer is no, because I have x squared plus 2. X squared plus 2 set equal to 0 gives us complex values, and we do not consider complex values as asymptotes. So there will be no va and no ha, because horizontal asymptotes and slant asymptotes are mutually exclusive. You can't have both at the same time. So for graphing this function, you only have this one asymptote to work with. Now we are going to have an entire section on graphing functions by hand, where we are going to compute a lot of stuff for something like this, and this talk of asymptotes is going to take about a fifth of that conversation, right? We will be calculating 13 different things, including domain, x-intercept, y-intercept, 3 asymptotes, and then derivatives and first, second derivative tests, critical points, inflection values, and all of that. That's 4.3. This story takes 3 out of those 13 points, 13 bullets that you have to go through in order to graph the function without calculator. And it's a very powerful technique. You will be able to graph ln of x squared minus 1 without a calculator. Try it now, see what happens, right? So we are building towards that. So I'm just making sure that you understand that this is going to be used later. And it's not just, okay, you know, get it now and then put it on a back burner. So that's the story of asymptotes, and that's the story of end behavior. And now we are just going to compute some of the limits to practice mechanics of working with these limits. So limit x goes to infinity of x squared minus 3x plus 1 divided by 3x squared plus 9. Now, some of you might already know the answer to this. Does anyone know what the answer is without doing any calculations? You should know it from pre-calc. Cover up the limit in your mind and tell me the horizontal asymptote by looking at the problem. What is the horizontal asymptote when exponents are the same? 1/3. So the limit of this must be 1/3. Now, clearly, if you plug in infinity, it's not going to work, right? because it would be infinity minus infinity plus 1 divided by infinity plus 9, and that cannot give you 1/3. So that's the wrong way to do it. However, there is a nice, neat trick that you can use, and that is divide each of the 5 terms by the x with the highest exponent. In this case, x squared. In the previous case over here, x cubed, right, would be dividing each one. So now we are going to remember to copy the limit, otherwise my allergies kick in. I become allergic to you. And then when you show up next time in class, you start sneezing, and then it's a problem, right? So make sure you write this limit every time. We have x squared divided by x squared minus 3x divided by x squared plus 1 over x squared. Then we have 3x squared divided by x squared plus 9 divided by x squared. So this is the step where you divide every single term by the x with the highest exponent you have in the entire problem. Now, this simplifies to limit x goes to infinity, and we have 1 minus 3 over x plus 1 over x squared divided by 3 plus 9 over x squared. Now, if you studied properties of limits, which was supposed to be on the quiz today, right? Properties of limits, you know that this limit will propagate to each one of these individually, right? So ultimately, what I want to know, and I have to write this in blood because it's extremely important, ultimately I want to know what is the limit of x goes to infinity, or negative infinity, of 1 over x to the n. What is that? What do you think? You can start with x to the first power, so just 1 over x, and then the second and the third and the fourth, and they all give you the same answer. What is the answer? 0. Because if you draw 1 over x, you see that this side goes to 0, this side goes to 0, whether you put positive or negative infinity. If you draw 1 over x squared, which looks like this side goes to 0, this side goes to 0. X to the n goes to 0. End of story. Which is the reason why each one of these dies, and the only thing you have left is 1/3. Now, you were asked to memorize that in pre-calculus 1, which is the reason why you are clueless now. Because anything that you memorize, it evaporates. If it doesn't have a purpose, if it's not connected to the concept, right, it's just gone. Why would you remember it, right? So I'm not saying you are bad because you remember it. It's just a fact of nature that you are not, I can't expect you to remember it, right? It's been a year since you looked at that stuff, first of all, right? It's not something that you use on daily right routine to survive, like, you know, tying your shoelaces or driving. So, you know, but now when you have this new mathematical concept, see, yeah, not a big deal that you forgot, because now you know the way to get it every time you need it. So those of you who remember the shortcut on exam might just go and write 1/3. It's full credit, right? And others will work out the problem and get 1/3 after, you know, the next 2 steps. So now let's make this interesting, right? Oh, actually, before I make that interesting, let me elaborate on the red stuff I wrote over here. Please note that this is the answer, right? This is the answer. Let me rephrase it. What you get, all right? And I have to use that phrase. Now I have to go and check that printer, see if there's a paper in front of the printer. We're going to do an experiment now. Behold number 1. That's this. You have one piece of paper. You have one watermelon, right? Whatever it is. That's what number 1 is. And you are going to divide that by 2. So, you are dividing by 2. Which means you are cutting the paper or the watermelon or whatever you are dividing by 2, you are cutting it in half. What is the answer? What is that the thing that you have as a result? When you divide 1 by 2, you get a half on the other side. Now, size-wise, what you get is smaller than the 1 unit you started with. Now, if I take that answer and I divide by 2, I get a quarter. And I divide by 2, right? I get 1 over 8, 1 over 16, 1 over 32, 1 over 64. There are 64 of these in a big paper that I started ripping. 1 over 28, 1 over 256, 1 over 512 of these in a single paper, right? Now, where is this going to go as I keep dividing to infinity? I divided this, 10, 15 times, right? Where is this going to go? Where is it going? I can barely hold it as this goes to infinity. Right? Does it make sense now? Yeah, it should make sense, right? So, when you have this situation, maybe I should continue making confetti over here and then at the end of the class go, right? So that's the idea, right? And there is another one that is also another limit that belongs in 2.4 that I need to discuss now. And that limit is where you have 1 over x as x goes to 0, right? In which case you are getting infinity. So let's box this one blue and say 2.4 because right, this is infinite limit. Infinity is in the answer. So now when you're looking at these two are big calculus tools. We are going to refer these a lot to these. To understand the second one, I don't know if you ever short-circuited the outlet and caused a little explosion, a little puff that is very uncomfortable and scares you, right? Sometimes the light bulb explodes like that because it gets shorted. Why would that happen? Well, it's actually the one in the blue box. You have the Ohm's law, which says that current is equal to voltage divided by resistance. And for most part, we have 110 volts, which is steady. Well, it's 118 to 120, and then voltage drops when you plug something in. But let's keep it at 110, all right? And if you have something that it's, let's say, 55 ohms in resistance, you get 2 amps, and this is the standard consumption for your chargers for cell phones. There are 1 amp chargers, those are slow, and then you have 2 and 2.1 and up, right, for fast charging. So it requires that the solenoid inside, which is a transformer side, to have a resistance of 55 ohms. However, if you go and short circuit your outlet, meaning your resistance, so we are getting the limit where R goes to 0, the answer is infinity, right? Because what is this function? This function is 1 over x function. You know what that looks like. So as you are going to 0 from the right, you see that this part goes to infinity. Now, if current is going to infinity and current is proportional to temperature, in the infinitely small interval of time, current wants to go to infinity, temperature goes to infinity. So if the energy in a very short interval of time is trying to reach infinity, we define that as explosion. That's what it is. No, that's the definition of explosion, actually. Mathematical there is a whole branch of mathematics, guys, called mathematics of detonation. And there are people, researchers, that work in that field. And they're employed by government and defense companies and so on. That's a real field of mathematics. It's called mathematics of detonation. This is the first principle you learn in that course. There's a field. So, by learning, these basic ideas, you get to describe and understand the world around you. So anytime you short circuit the outlet, or you take the 2 prongs of the battery and just put them together and go spark. If you do the things wrong, now that one is very dangerous if you're trying to jump the car, because that one can actually kill you. This one pretty much can't kill you, but the one on the car is a direct current, and that's, if you know anything about chemistry, DC current is much, much scarier than the AC current. Much scarier. Much lower voltages for certain death. So you put 2 car batteries together, should be enough, more than enough. And that's only 24 volts. Where 110 over here, I've been hit so many times by 220, this is why I'm like this, all right? Where I come from, it's 220 in the outlet. And then you have 380. For the higher voltage. In US is 110 and 220. So if you have a little lamp like this with a conventional bulb inside, that's how I found out that the graphite is an excellent conductor of electricity. So I was, I think, 8th grade or something. I was tinkering with electricity, been hit so many times that I know very well the tingling feeling when 220 hits you. And the light bulb was missing. I was working on my homework, and for whatever reason, and I had the a pencil with the graphite inside. For whatever reason, I decided to stick the pencil inside, and you get immediate bzzz. Then I said, well, and my father was an electrical engineer, so I said, why did I get shocked that the wood is supposed to be insulator, right? Because you learned that in school. And he said, yeah, but the graphite is not. It's one of the best conductors that there are. We're not using it because you can't bend it, right? That's why you use the metal. But graphite is much better conductor than the... So, you discover things that way. That you have to, you have to do stupid things. Don't. Public service announcement. So yeah, there you have it. So these two concepts, right, related to making confetti or creating small explosions. I think we can do a few more examples to take a look at mechanics of solving problems, because you might be interested in that as well. I don't think we might have something else. If the book would load, that would be great. I mean, I can always check by, oh, there we go. We're sorry, but something went wrong. Clearly, if I can't see what I'm looking for. You call someone, get a machine. Sorry, I can't come to the phone. Really? Like, you don't need to tell me that. My IQ is more than 70, okay? I get the concept. Just say leave a message and have that beep go and rip through my ears, and that's that. No, we're done. Okay, so let's do a few examples. No more concepts. We covered everything. Let's work on a few problems few spicier problems, we already did the vanilla ones. Oof. Nice. Let's go with find all asymptotes. I'm always sad to deduct points where I say find all asymptotes and vast majority of you and all of you right go, vertical asymptote here, horizontal asymptote here, next problem. And I just say, was one missing? Which one is missing? Slant, exactly. So don't discriminate, at least try to be, try. Give it like a shot. So let's see, problem 40 is good. So find all asymptotes on 40. Function is f of x equals, in the numerator, you have 3x squared minus 2x plus 5. And in the denominator, you have 3x plus 4. Have fun. Okay, let's go in order. Vertical asymptotes first, right? So we need to, for candidate points, we need to set denominator equal to 0, from where x equals -4/3. And we need to make sure that those -4/3 there we go. We need to show that those -4/3 are not cancelled. For instance, this might be factorable so that this cancels. In that case, you have no vertical asymptote. We talked about it yesterday. If the denominator cancels, you don't have a vertical asymptote. If you have multiple points, candidate points in the denominator as vertical asymptotes, and some of those cancel, those points are not vertical asymptotes, they're open circles. So the fastest way to check is to actually plug 4/3 here. If it gives you 0, that means it's a root, which means 3x plus 4 is a factor, if you learned your pre-calculus. If you know nothing of that, then just go and factor and see if it cancels. In my case, since I know factor theorem and other things from pre-calc, I am going to plug in and get 3 times 16/9 minus 2 times plus, and then over here times 4/3, and then plus, I need 15/3 for common denominator. This cancels to 3, so it doesn't cancel. As you can see, they're all positive. They all add. There is no way to go to 0. I don't even care what this adds to. It's not going to be 0. So yes, there is a vertical asymptote here, and this is the way to bypass doing the limit, right? So there is a vertical asymptote at -4/3 because 3x plus 4 did not cancel. If it cancels, it's not a vertical asymptote, it is open circle. Now, I used pre-calculus witchcraft rather than calculus, but, you know, it is what it is. For horizontal asymptote, I can cheat again. And I can say the degree in the numerator is bigger than degree in the denominator. This is the rule that you memorized in your pre-calculus, and claim no horizontal asymptote. However, I am going to do the limit for this because this is what we studied today. So I'm going to check limit x goes to infinity. And I know that I need to divide by the highest exponent, which is x squared in this case. So I have to divide everywhere by x squared. Which gives us limit x goes to infinity. When we cancel, 3 minus 2 over x plus 5 over x squared divided by 3 over x plus 4 over x squared. Observe what happens. 0, 0, 0, 0. You are getting 3 over 0. That's not a finite value. We know that, right? 3 over 0 goes to infinity, right? So, equal to not finite, therefore no horizontal asymptote. Since these are polynomials and we have the rule where the top is bigger by 1, we are going to, for slant asymptote, we are going to do the long division of polynomials. So we have 3x plus 4 divided into what? 3x squared minus 2x plus 5. Three x goes into 3x squared x times. When I multiply back, x times 3x is 3x squared plus 4x, and then I need to subtract. These cancel. I get minus 6x, and then I bring 5 down. 3x goes into negative 6x negative 2 times, and I don't have to do anything else. I don't care about the remainder. I don't care about anything else. I have my equation x minus 2. So slant asymptote at y equals x minus 2. So horizontal asymptote none, vertical asymptote negative 4/3, slant asymptote x minus 2, and actually that is a lot of information for you to graph a function already. Because, again, all of this again in 4.3. So we have x minus 2, this is minus 2, x is the 45 degree. So our slant asymptote is at 45 degrees. I'm just adding extra stuff. They only asked about asymptotes. And then we have a vertical asymptote at negative 4/3. That's over here. It's like 1 1/3 on a negative side. It's like negative 1.33333. So now, your function is either going to be like this, it's going to be like that, right? That depends on the other things that you find, because you might find no x-intercepts. Well, you clearly can't draw this because you just made an x-intercept there, right? So if you calculate no x-intercepts, then the function goes here and here. You know, there will be extra stuff to do, which is the reason why we have 4.3 as a separate section. But, you know, this calculation that we have here, the problem 40, becomes that, you know, that little part, like the, you know, the 3 points of 13 points that you have to work on. All right, let's see. Sheesh, nice. Find the limit as x goes to infinity. This is problem 41. For 4x cubed plus 1 divided by 2x cubed plus square root of 16x to the 6 plus 1. And if anyone goes, but why? Because we can, all right? Can anyone tell me the answer just by looking at this? It's obviously 2/3. What is the method that we learned? How do we find the limit? Divide by the x with the highest exponent. X with the highest exponent is x cubed. Very good. Yeah, I know you are all staring at the 6 over here, but the square root of 6 is 3. So, right? I mean, square root of x to the 6 is x cubed. So it's x cubed all around. Right? Right. All right, good. So you divide everywhere by x cubed. And you will end up with 4 divided by 2 plus 4. 4 divided by 2 plus 4 is 2 over 6. 4 over 6, which is 2/3. Now, very important thing over here is when you're dividing in the square roots to divide by x to the 6. Because when x cubed undergoes the square root, it picks up double power, right? You are used to the fact that the square root of x to the 4 is x. Let's do 3, right? So x, right? X to the 4th will go outside as x squared. Well, if I need to stuff it back in, the square root will double the power. So if I'm dividing everywhere by x cubed, and that x cubed has to undergo square root, well, it will pick up double the power, and that's why 6 shows up. So now when you cancel everything, you get 4 plus 1 over x cubed, and then you get 2 plus square root of 16 plus 1 over x to the 6. Now when you apply the limit, as we did before, like 1 over x to the n, so all of these go to 0, and right, the limit will kill them, and all is left is 4 divided by 2 plus square root of 16, which is 2/3 when you compute. And just, you know, because we can, limit x goes to infinity of sine x is equal to does not exist, to see one of those as well. It oscillates, right? It oscillates between -1 and 1, goes as a sine wave forever. So that would be one of the cases when you have does not exist. It has to oscillate like so. Cosine would produce the same. Tangent would produce the same. I mean, all trig functions at infinity because they are periodic. And that's what is so special about trigonometric functions. They repeat after a period. So all of the limits, so limit x goes to infinity of a trig function does not exist. But you have to be very careful. It does not work the same for inverse trig functions. Inverse trig functions do have these limits, some of them. So for instance, if you write limit x goes to infinity of tangent x, you are going to get does not exist, because tangent will have these going like that forever. And you don't know what value you hit. For the inverse trig function, limit tangent inverse of x as x goes to infinity, you are getting pi over 2. And you have to be very careful about these things. The graph of the inverse function for tangent looks like that. And guess what? Has the horizontal asymptote at pi over 2, hence the limit. Because this limit is for horizontal asymptotes. So that's the top, pi over 2, giving us the common sense on the bottom. X goes to negative infinity of tangent inverse of x is negative pi over 2. You can also blame this on it being an, what do you call it, the odd function. So you have negative pi over 2 horizontal asymptote. And this is the problem that has 2 horizontal asymptotes, and the function is stuck in between them. So that would be that. I also mentioned, or did I mention logistics growth? Yes, I did, in the first day. Logistic growth for population, right? That's one of the exponential functions, and that one would have a carrying capacity, which is, again, horizontal asymptote. You let the population you let the time go to infinity, and you ask what's happening with population. It is insane to take the basic exponential model and say, yeah, if I wait, long time, there will be infinitely many people. No, they won't, right? Because we need food and energy and space to occupy, right? And the planet has the finite area. The population issue is huge. People don't get it. The population crisis that we are experiencing right now, it's not still manifesting itself to its full, but it's insane of what kind of trouble we are at currently. Because we are experiencing exponential growth in population. And exponential growth is much different than what we are used to, which is linear growth. There is a very cool exercise that we can practice real quick if you want to understand how doomed we actually are and how much 5 to 12 actually it is right now. Well, it's actually 2 minutes after 12. So, yeah. All right, so that's that. We'll come back with continuity in 5